We can now move to the lesson number 6, that is about many-body quantum systems of identical particles, both bosonic and fermionic. Obviously, we have seen the case of identical bosonic particles within the quantum electromagnetic theory, but now we will extend the approach also to massive particles, both bosonic and fermionic, but considering the non-relativistic case, because in condensed matter physics, usually apart the light, the matter is well described by non-relativistic theories, because the velocity of the particle is very small compared to the speed of light. Let us start with this unit 1 of lesson 6. So I will share the screen, full mode. Okay, the title of this unit is Identical Particles, Bosons and Fermions. We can start from the generalized coordinate x of a particle, which takes into account both the spatial coordinates denoted by the position vector r, but also the intrinsic spin sigma pertaining to the particle. So for simplicity, instead of using both vector r and sigma, we use a simplified symbol x, which is which correspond to both space coordinate and intrinsic spin of the particle. For instance, for a spin 1/2 particle, this sigma corresponds to the third component, and so it can be -1/2 or +1/2, or if you want, up and down. By using the Dirac notation, the corresponding single particle state can be written as ket x, where obviously this actually means ket r, bold R, sigma. Now we consider n identical particles, for integral particles with the same mass and the same electric charge. Well, if you want, all the electrons are identical, but maybe you can also have, I don't know, a gas of rubidium atoms, and if you consider each atom as a particle, effective particle, if you have 1,000 rubidium atoms, they can be considered as identical because the mass is the same and the charge, if they are atoms, the charge is 0, is the same. In general, the many-body wave function of this kind of system of identical particles can be written as psi, for instance. We use a capital psi, actually, to denote the many-body wave function. And obviously, it is a function of the coordinates of the particle. In this case, the generalized coordinate of the particle. So this capital psi is a function of x1, x2, x3, x4, etc., up to xn. Obviously, this means that the psi is indeed a a function of the coordinate of the R1 and the spin sigma 1 of the first particle, the coordinate R2 and spin sigma 2 of the second particle, etc. According to quantum mechanics, identical particles are indistinguishable. As a consequence, the equation 3 must hold. Namely, if you do the square modulus of this many-body wave function, or the square modulus of the same many-body wave function where you are interchanging two generalized coordinates. Here, for instance, you see on the left we have in between, on the left and in between the argument of the wave function, we have first x I and then xj. If you exchange these coordinates, putting xj instead of xi and I instead of xj, you must find the same number. This means that the probability of finding the particles must be independent on the exchange of two generalized coordinates. Experiments suggest that there are, well, instead of only, could we better say at least two kinds of identical particles which satisfy equation 3, which are bosons and fermions. There are also other particles, more exotic particles like anions, but we will not consider in this course anions. So, for n identical bosons, we have the same formula of equation 3, but without the square modulus. So the wave function without the square modulus is such that if you exchange two of the generalized coordinates, you get the same wave function. This means that the many-body wave function is symmetric with respect to the exchange of two coordinates x and y. Notice the difference. I repeat, here you have the wave function. Instead, in the previous formula, you had the square modulus of the wave function. So for the bosons, equation 4 holds. For n identical fermions, one has instead that exchanging two generalized coordinates, a minus appear. So equation 5 holds. The many-body wave function for fermions is antisymmetric with respect to the exchange of two coordinates xi and xj. An immediate consequence of the antisymmetry of the fermionic many-body wave function is the Pauli principle. In fact, if xi and xj are equal, then from equation 5, one immediately finds that the object on the left must be equal to minus the same object that is on the left, and this means that is 0. So one finds the Pauli exclusion principle, namely the many-body wave function must be 0. So if you have two fermionic particles in this with the same generalized coordinate, the wave function is 0. So this means that the probability of finding two fermionic particles with the same, exactly the same generalized coordinates is 0. This is indeed the Pauli exclusion principle. That is a principle in the initial formulation, original formulation of Pauli, and here, if you want, becomes a consequence of the definition of identical, the many-body wave function of identical fermions. A remarkable experimental fact is, which is also called spin statistic theorem, because it can be deduced from other postulates of relativistic quantum field theory, is the following. Identical particles with integer spin are bosons, while identical particles with semi-integer spin are fermions. For instance, photons are bosons with spin 1, while electrons are fermions with spin 1/2. If you have a composite particle, like for instance an atom, potassium atom, what is the spin of this composite particle? Well, the spin is in general the sum of the spin of the electrons that surrounds the nucleus of the atom plus the spin of the nucleus, which is obviously composed by the spin of the nucleus. The total spin is the spin of the effective particle that is like an atom. So if you have many identical atoms, you can say that they are identical if they have sorry, you can say that they can be identical and bosonic if the total spin of the atom is an integer of the Planck constant, and instead if it is a semi-integer of the Planck constant is a fermionic atom. This is exactly what is written here. Notice that for a composite particle, it is this total spin which determines the statistics. For example, the total spin sum of nuclear and electronic spin of helium-4 atom is 0, and consequently this atom is a boson, while the total spin of helium-3 atom is 1/2, and consequently this atom is a fermion. The quantum non-relativistic Hamiltonian of n identical non-interacting particles is given by equation 6. You see, this capital H naught with the hat is the sum of small h with the hat Hamiltonians, which are a function of the generalized coordinate x subindex I. You have to sum over I that goes from 1 to n. And this small h of x is the single particle Hamiltonian. Usually, the single particle Hamiltonian is the sum of a kinetic term plus an external potential term. Here, the kinetic term is written in first quantization, namely minus h bar squared over 2m nabla squared, where obviously m is the mass of the particle. Instead, the external potential is here denoted with the symbol capital U. Both the kinetic term and the external potential term depends on the coordinates, and in this case, actually on the space coordinate, bold r, which means the 3 spatial coordinates, and also nabla squared obviously means the sum of the second derivatives of the spatial coordinates. In general, the external potential can be also a function of the spin, but in this case I have not included it. In general, moreover, the single particle Hamiltonian small h with the hat satisfy the eigenvalue equation shown in equation 8, namely small h with the hat when applied to a function phi of x must give the same wave function phi times a number epsilon. And in this case, this phi is called eigenfunction and epsilon is called eigenvalue. Obviously, in general, there are many eigenfunctions and many eigenvalue for a specific single particle Hamiltonian. And for this reason, I put the subindex n just to enumerate the many wave eigenfunction and eigenvalues. So there will be, in general, epsilon n, that is the single particle eigenvalue or eigenenergy, and a phi n of x that is the single particle eigenfunction, the corresponding single particle eigenfunction. The many-body wave function capital psi, function of x1, x2, etc., up to xn of our system, can be written in terms of the single particle wave function small phi, subindex n of x. But one must take into account the spin statistics of the identical particles. For n bosons, the simplest many-body wave function is such that all the particles are in the same single particle wave function. So your capital psi, that is a function of x1, x2, etc., can be written as the product of a single particle wave function, but which are the same. You see, there are the subindex of phi is the same, and obviously each wave function depends on its own generalized coordinate. Here you have x1, x2, xn. In practice, this means, for instance, if you have an harmonic potential with many single particle levels, for bosons, you can put all the particles in the lowest single particle energy. Obviously, all the particles have the same single particle wave function phi 1, say, but they could have different space positions, but the phi is the same. In this case, you have a pure Bose-Einstein condensate. And this is exactly what is written in equation 9. In the case of Fermions instead, the simplest many-body wave function is much more complicated. And it's given by this expression here, where you see we have on the right the many-body, on the left, sorry, the many-body wave function, in the left of the equality, and on the right of the equality, you have 1 over the square root of n factorial. Remember that the capital N is the number of particles, in this case, number of bosons, fermions. And then you have the determinant here. There's somehow that is missing. This is the you have to calculate the determinant of this matrix, and this is called, obviously is a scalar. This is called Slater determinant of the n by n matrices obtained with the n lowest single energy obtained with the capital N lowest energy single particle wave function. This is wrong. This should be phi subindex n of x with n that goes from 1 to capital N, calculated with the n possible generalized coordinate x subindex I, with I that goes again from 1 to capital N. You see, in this matrix, you have phi 1 x1, phi 1 x2, etc. Phi up to phi 1 xn. In the second row, you have phi 2 x1, phi 2 x2, etc. up to phi 2 xn. It's many others, and the last is phi capital N x1, phi capital N x2, etc. up to phi capital small subindex capital N of x subindex capital N. Why this? Because the determinant has the correct properties of fermionic wave function. Namely, it is antisymmetric if you exchange two elements. And that's why it's the natural way to write a many-body wave function, because the determinant here, again, repeat, that is missing, is the has the crucial property, namely, if you exchange two elements of the matrix, the determinant changes sign. And if two elements are equal, you get 0. Pictorically, you can again think to an harmonic potential with many energy levels, but if you have fermions, actually somehow spin polarized fermions with the same spin, you can have at most one fermion per single particle energy level. So this is the lowest single particle energy level, one fermion, this is the first excited, one fermion, second excited, another fermion, etc. Up to the higher occupied. By the way, the higher occupied single particle energy level of fermions is also called Fermi energy. Obviously, for bosons left, the total energy, if the bosons are in the Bose-Einstein pure Bose-Einstein condensate, is simply the energy of the lowest single particle level, epsilon sub index 1, times the number of particles. While for fermionic many-body wave function 10, the total energy, in the absence of the generate single particle energy levels, is given by equation 12. Namely, you have the energy of the lowest single particle level, plus the energy of the first excited, plus the energy of the second excited, up to the highest excited single particle energy level. And obviously, this means that the energy of non-identical fermions under the same external potential of bosons is higher than the total energy of the bosons. As previously said, the highest occupied single particle energy level is called Fermi energy, and usually indicated with the symbol epsilon sub index F, or as in the figure, capital E sub index F. In our case, obviously, this epsilon sub index F, the Fermi energy, is equal to epsilon sub index capital M. In the next unit, we will consider the more detail the properties of identical fermions confined in a box, and we will derive for them the explicitly the Fermi energy as a function of the density of the fermionic particles, and also the total energy of the fermionic system as a function of the density.